Right, so this is the office hour for before the quiz. So I'm going to record it. And I asked the students to ask some questions on chat window so I can see those, but I didn't write it here. Um, but anyway, I see the questions, but Kristen or whoever want to go first, just say the questions.
Yeah, so my first question was, when do we use the equation given for AB in lecture 9? It's like slide 24, 25.
Give me a second, let me open the lecture.
And this is specifically referring to homework question 1B. When we solve for like V naught, velocity overflow rate, it gives the equation as Q over AB. But when you solve the question, you don't use the equation for AB given in the next slide.
Oh, so this is the questions about the slide number 25 and 26, right? In the lecture note. So
Yes.
the question was, when we use the equation for AB? AB is basically, AB is the clarifier area, right? The surface area. Um, so, so let me write the question here because people don't know what we're talking about. So if you think of a clarifier, and if you wanted to know the area, that area, this area, if you create overflow rate, velocity of overflow equal to velocity of settling, then if you solve for area, that gives you this number. Area equal to 18 times flow rate times viscosity, acceleration due to gravity, particle density minus density of water, and particle size square. So the question was, when are you going to use AB? So you got to know what does that mean, AB. AB means you are assuming the size of particle as dp, right? So what it's saying is that this is the minimum area needed for to remove all particle with the size dp. Okay. So if somebody asks the questions, what is the area of for a clarifier, so that you remove a particle of certain size, this is where you will use the equations. But now if you're let's say another, that's just the one thing. And then how homework question 3, why don't we use connect? Okay, so that's a different question. So does it answer these questions? You are only going to use this equation only if your assumption is 100% of particles are removed. Okay, and this is AB is the minimum area needed to remove particles of size dp or larger. Okay. Christine, does it answer the question, or I move it to some other directions?
Yeah, I think that makes sense.
Okay. The second question, Kristen, do you want to repeat that?
Yeah, my next question was referring to homework question 3E, and I was wondering why we don't use the concentrations of calcium carbonate when solving for total dissolved solids, because you're adding the concentrations together, so I thought they had to be in terms of the same chemical.
Okay. So that's related to homework 5, right? So it says that why don't we use concentration of calcium carbonate solving for total dissolved solid? So let's think of what is total dissolved solid. Total dissolved solid in any water. So let's say you have water and you have sodium, you have chlorine. I'm just throwing all the number, okay? Magnesium, calcium, let's say CS CO3 SCO3 minus. So you have lots of this amount here. If I ask what is total dissolved solid, that means if you imagine that you are going to boil this water, when you boil, all the water is going to evaporate. Everything that remain in that pot will be the salt. Okay, so that's what it is. So if you remove all water, salt precipitates. So that's sum of all salt. Okay, so that's dissolved solid. What does that mean? So that's basically total dissolved solid, because it becomes solid after you evaporate all the water. So what that means is, if you know the concentrations, then you just add up everything. Let's say I'm just throwing a number, NaCl plus Ca CO3. I'm just throwing a number. I'm not saying this is the salt would be. If you know the amount S per solid, then this will be total solid, right? So what you are doing is you are just looking for how much milligram per liters of each, okay, and then you add it up together, and that's what becomes. Then you get the answer in milligram per liter. That means if you take 1 liter of water, and if you evaporate everything, that's the milligram of salt that remain is here. So the actual definition of TDS is milligram per liter of salt. So if you know exactly how much weight of each salt is, then you can add them together. But in this case, you don't know, because you know only the individual species. You know the sodium concentrations and magnesium concentrations. So when you add them up, then that should be the total salt amount, because you are saying weight of that sodium. So as you know, mass balance, you can add the mass, right? Because you are not looking for the reactivity here. You are just adding of the mass. So that means you can add milligram of sodium with milligram of chlorine, because I'm asking how much weight of that's together. I'm not asking reactivity. So that's why usually the concentrations is given in milligram per liter. So in this particular case, if you know sodium concentration, magnesium, calcium, all those things, just add them together and you should get milligram per liter, because you can add, mass can be added. Um, but sometimes, if I specifically ask, what is the concentration TDS as CaCO3, milligram per liter as CaCO3, you should take this as any other questions. If I ask what is milligram per liter of nitrate as milligram per liter of nitrogen, you know how to convert that. The same thing here. Okay. So I think, if the question asks what is the TDS, just add them together of milligram per liter and then you are done. If I ask you as calcium carbonate, then you would do that. But normally you don't need to use calcium carbonate, because it's not needed. It's not reactivity, it's just summing of weight. Does it answer the question, Kristen?
Yes. As a follow-up question,
Yeah.
um, so you would use TDS to find the weight of salt in a particular volume of
Yes.
water.
Yes.
Okay. Thank you.
So basically, you're adding weight up, okay? Because if I add one pen, another, let's say this mouse, I'm asking the total weight. So they can be added, even though they are two different things, because you are looking for a parameter that can be summed. Okay. Before we could not add them together in a reaction, because reaction is, it implies that one of these things will react with another one of this. So that ratio is important. So reaction has a different reacts. When you add things in a reaction, you have to think of molarity and normality, all that stuff. But when you're adding the weight, it doesn't matter.
Thank you.
Right? Um, any any other questions? Next question, I see Sabrina's questions.
My question was, how do we solve for the fraction of, this is pertaining to homework 5, 2B.
Okay. So let's say any question. So any question I ask, you know the size of a clarifier, and I ask, you know the flow rate, you know the particle properties. So particles, you know the particle density. Let's say you know the particle size here. Okay, these are all given, right? And the
Yeah,
size dimensions are also given. So this given, these are all given. The dimensions, everything given. And I ask what's the removal, how much percentage will remove. So think of this way: if overflow rate, velocity of overflow, so that's over, and then you have another thing is sedimentation rate. Okay, the velocity of particles when the sedimentations or sedimentations velocity. So these are the two things you can calculate. You know, if v0 equal to vs, that means all removed. Okay, because before it become, before it overflow, everything already settled. Okay, that's sufficient enough time. Or I'm going to write this one: if v0 less than equal to, that means, let me think of this way: if your velocity of overflow rate is lot slower than the sedimentation velocity, everything else will be removed because you are sedimenting much faster than it overflowing. Okay, so the minimum is equal. Once it's equal, it's all removed. Even after that, it doesn't really matter. It's only when v0 is greater than vs, not all removed. Okay, because there is a certain fraction. What you are saying here is this is the overflow rate. You are overflowing water much faster than you are letting the particle settle. So that means particle doesn't have enough time to settle before the water overflow out of the system. So that means some particle will carry over in the effluent. So now question is how much particles. That's all about is comparison. So as I said, so your reference point is v0. So if the vs, when it's equal to 1, all removed. When vs by v0 is less than 1, not all removed. When it's the case here, okay, because v0 is greater, so it becomes less than 1. That means vs by v0 is the fraction, the ratio is the fraction removed. If you see the slides, I'm going to show you, I'm going to check the slide where I wrote this one. That's on slide number 27. Percentage removed equal to vs by v0 times 100. So you just have to calculate vs for the particle size of 5 micron. And your v0 is a design. It's not changing because of particles, more about the flow rate and size. So you just substitute that value here and you get the answer.
okay, thank you. Yeah, I saw that on the slides, but I wasn't sure where that came from, so I was a
Okay.
little confused.
Yeah, so it's all about like you are comparing whether you are settling at faster rate than you are overflowing. So that
Oh,
ratio is always the percentage removed.
okay, I see.
Okay.
And my next question was for also homework 5. It was
Okay.
for 4A. Are we assuming that the concentration of cations is equal to the concentration of anions? Because in the previous question, we had the concentrations of each ion, but in terms of another ion, but this one, it's just given to us directly, and it's in a sample of water, so I'm not sure.
So let's see, charge. So your question is, does the concentrations, I'm going to write it here, anions in a solution, if you take a solutions that you want to, like I said, Na plus, Ca plus, 2 plus, magnesiums, Cl, SCO3. So these are, so you're asking if concentration of all anions would be same as concentration of all cations.
Yeah.
right?
Mhm.
Yes. The reason is you do not have any the like mass balance. There is always charge balance. So now how do you do charge balance? Let's write this one. If you know the concentrations, let's say write this one. All positive charge, so add them together. Okay, should be
Mhm.
equal to all negative charge, right?
Oh, okay.
The but here is the trick. This is not the charge balance equation. All I'm saying
Mhm.
is all concentration. You are adding concentration. You are not adding charge here. But I ask you charge balanced. Okay, charge balance means you have to account for how many charge in that concentrations. So if you have 1 moles of calcium, it gives twice as much charge as 1 mole of sodium, right? You have
Mhm.
to multiply that charge here, then it becomes charge balance. Only when you do this one, then you can solve for that question is given sodium. You can only solve if you have this way. Okay. So charge balance is sum of concentrations um, of all the positive charge should be sum of concentration of all negative charge,
Mhm.
including you have to account for number of charge in that concentrations. So that's why I because this is plus one charge, I didn't write one here because it doesn't really matter.
Mhm.
Okay, so we are looking for number of charge. So 1 mole of calcium has 2 moles of charge plus charge. So you are writing charge here, moles of ions.
Okay, thank you.
Okay.
Sorry, I have a question based off of that.
Okay.
Um, so when you calculate concentrations as like CaCO3, you does does that account for the charge? Because you always have to like divide it by the number of charge, right? So like, what does that do for the concentrations?
So think of what is concentration means. You are asking. Can you repeat the question? I don't want to think.
So when you calculate things in concentrations of milligrams per liters of
Okay.
CaCO3, you
Okay.
always divide it by the charge of each ion. So I was just wondering what that does for the concentrations instead of just dividing like per molecular weight.
Okay. So let's say I'm just sake of simplicity. I said bicarbonate or FeO3 concentration is 100 milligram per liter, right? Uh, so you are saying that do I divide by charge here?
When you convert it to like
Okay, okay.
milligrams per liter as
As okay, okay,
CaCO3.
okay. So when I convert that to as milligram per liter as CaCO3, then I always divide by charge, right? That's what you are saying.
Or it's always like the molecular weight of CaCO3 divided by the charge, and then over
Charge,
that
yeah.
is like the molecular weight of like each
Okay,
CO3
yeah.
divided by its charge. So I was just wondering, why do you always have to divide it for that charge for both of them? Is that
Okay,
supposed to
okay.
account for charges, or like what does that do?
Oh, I see, I see. Okay, got it now. So let me write the formula. If you're writing milligram per liter, let's say any species, milligram per liter as CaCO3, and you are trying to convert that from milligram per liter of X, you always write this formula, right? Milligram, or let's say molecular weight of CaCO3 divided by the, let's say, NCaCO3. This one, right? This one, and then molecular weight of X divided by N of X, right?
Mm-hmm.
Okay, so you are saying why we are doing this one.
Yeah. Or
Okay.
I thought I was to account for the charges, but because
No,
you
it's
explained to Sabrina, I
yeah.
thought that maybe my thinking was wrong.
No, it's not about charge actually. It's about actually what we are doing here is milligram per liter of X times equivalent weight of CaCO3 divided by equivalent weight of X. That's what we are doing. That's the real formula. Equivalent weight means, so think of this way. If you are expressing one with another, you have to always say how they are equated. One equivalent, one equivalent of anything is another equivalent of same thing, because it's all about reactivity, right? So one react with another one, then it's equivalent weight is same. So um, like I said, what is equivalent weight? Equivalent weight, it says the reactivity, how much it was the reaction power of it. And that's usually molecular weight divided by charge, because number of charge means number of reactions. Okay, if you let's say the calcium carbonate, it has 2 plus charge, that means it can take 2 protons away from
Mm.
somewhere else. So that's why the n equal to 2. And usually it's translated as charge, because that's what the means the reactions. Uh, and the reason we do it is because these are equivalent, these are comparable. Okay, molecular weight is not comparable between materials. Only equivalence weights are comparable. Only
So
how
then,
to, yeah.
when you like try to find the amount of what's it called, sodium,
Hmm.
because after you convert it to CaCO3,
Hmm.
doesn't that also like take into account the amount of reactions it can do, or does it
Yeah,
not?
so you're right.
Because
So when you do everything as calcium carbonate, you are basically equating everything as same species. So
okay,
equivalent doesn't matter, right?
okay, so
So
you
if,
don't have to, if you convert everything to
yeah,
CaCO3, you
you
don't
don't have
have
to do
to
it.
account for all the. Okay,
No.
thank you. Sorry, I was just a little confused about that.
Okay, okay. Yeah, so let me write it up. So this is here if milligram moles per liter. Okay, because moles per liters are not comparable. But if
Okay,
you don't have to account for charge, if you already have written everything, if everything is written in the same units, for
okay,
instance, unit which is comparable, if you already write this was as equivalent per liters or milligram per liter as CaCO3, do not bother about charge, because you are adding up calcium carbonate. All calcium carbonate has same charge, so it doesn't really matter.
thank you. Sorry.
Yeah, that's a good question. I think that's a very important conceptual question. Any other questions from homework 5? Because we are talking about homework 5, we rather finish this one before we talk about anything else.
I had a clarifying question. Um, so when we're solving for question 4A on the homework, we would have to multiply the concentrations of um, by 2 if it has a plus or minus 2 charge. Would we also have to multiply by 2 when solving for parts C and D because they also have a plus or minus 2 charge?
Are you asking about homework 5?
Yeah, homework
Homework
5
5,
part,
question
or
4.
yeah.
It's saying you have to multiply the constant of sulfate, calcium, magnesium by 2 when balancing the cation and anion concentrations. Um, so if you're, as I said, if you are using the units as milligram per liter, you do have to do. Okay. Um, okay. Let me put it back. You cannot add milligram per liter in charge balance. It's always molarity. Okay, moles. If you have to convert them as moles per liter, then only you can add them together. You can't add 1 milligram per liter to another milligram per liter, because it's not milligram of charge. Okay, charge is related to moles. So the way to do this one is you have to first change to same unit, similar unit, so that you can at least add. Um, so if you're changing the unit to moles per liter, then you have to account for charge. If you are changing the all the unit to calcium carbonate, milligram per calcium carbonate, your let me write this one, charge balance. This is for question number 4. Okay, charge balance for a species expressed as equivalent per liter or milligram per liter as CaCO3. So when I say equivalent liter, it doesn't matter really charge because that's already accounted for. Then the then you just have to write all them all together. Na plus A plus should be equal to SCO3 minus. Okay, because you have already accounted this for the things. But let me double check just quickly if I don't want to give a wrong information, because I didn't solve the question yet. um, but let me see my notes somewhere.
So we don't have to multiply by the charge if we're
If
using either equivalents
yeah,
per
if it is
liter.
equivalent per liter, you don't have to, because equivalent liter already the concentration already accounted for the charge, because you are using molecular weight. Because if you think of the very first quiz, 1 mole of calcium is equal to 2 normal calcium, right? Because the twice the charge. So this two normal is equivalent. Normality is equal to equivalent per liters.
But
So
what if we use milligrams per liter as calcium carbonate?
you can't use milligram because you can add milligram, because 1 milligram of positive charge doesn't mean anything, because charge is associated with one molecules or one atom. Um, so you can use a milligram per liter in any question related to charge, because if you think of 1 mole, what is charge means? Charge is associated with one atom, right? And one atom weight is different for different ions or different species. So when you say 1 milligram of calcium, it doesn't mean much when it comes to charge. So that's why I have to convert them to moles per liter. Or in this case, if you are already changing to calcium carbonate, then it's already there. You can just use that. You cannot use a milligram per liter in the charge balance.
So you cannot use milligrams per liter as calcium carbonate.
Milligram per liter as calcium carbonate, not milligram per liter as given in the book directly. You can use milligram per liter as CaCO3, not milligram per liter, because if you see the table given to you in this book, that's given 40 10s, all that stuff. So you can't use that concentration. You have to first convert them to calcium carbonate before you do the charge balance.
Okay, so if we use milligrams per liter as calcium carbonate, we
Yeah,
do not have to multiply by the charge.
you do not have to. Let me just confirm from my note.
Okay.
Which question it is? Question 4. Okay. Yeah, you don't have to. So what you have to do is you have to, this is the equations, and the units are CaCO3. Okay. And then you solve for it. That way you get the sodium concentration as CaCO3, right? And so when you solve this one, this the only unknown is this one. Okay. And then you get the sodium concentrations as milligram per liter CaCO3. Then you convert them back uh, to milligram per liter as sodium. So this is the equation you'll be using. Not, you don't have to account for charge. So your question was before, would we be multiplying 2 when solving for part C and D? What is C and D? For C and D, the concentration, I asked for the mass, you have the equation directly given to you. So there you are using the charge. The reason is you are using moles per liter concentrations. Anytime, so think of this way, a lot of this, might be confusion. Anytime you are using moles per liter, okay, moles per liter or molarity, you have to account for charge. You have to account for charge in reactions. Anytime you are using equivalent per liter or normalities, both are same, or milligram per liter as CaCO3, um, then you, in charge balance, you don't have to account for that. But the question was in your second part of the question is, when you are looking for the concentrations of select lime and all that stuff, do you account for the charge? There is based on the reaction stoichiometry. Okay, so that number is nothing to do with the charge. It's most on the reaction stoichiometry. So they are not the same concept here. So you just plug the value in that equation, and that equation, that number, multiply 2 and all that stuff. If you remember, let me see which slide it is going to be. That is on. Uh, let me open the. I think you are asking question C and D of 4, number 4. So that is related to. Let's see the slide number. Let's see, guys, number. Yeah, so slide number 38, that's give you how much amount of soda ash. And slide number 37, it give you amount of calcium hydroxide or slime. There you have a number 2 in things. Those are nothing with the charge. It's mostly related um, to the reaction stoichiometry. So as long as you are using the concentration as calcium carbonate, you just don't have to think of those multiplications. Just use that in that equation. Does it answer the question, Kristen?
Yes, thank you.
Right. So most of the questions are nothing with quiz. The only questions that somebody asks about quiz is, Liana, can you explain specific yield in relation to porosity again? Okay, so that's the only questions related to um, specific yield. So think of specific yield. Specific yield means, let's think of porosity. That's the most easiest thing to understand. Imagine you have a container and you fill with that some materials which has no pore inside. So that means porosity is the pore space, remaining pore space. Okay, so this is the pore space, this is total solid. Okay, so the total volume is this. Okay, so this is total volume. Pore space volume is V pores. So that means porosity is Vp by total volume. Okay, so the amount of pore space inside it. And specific yield means, imagine you fill with water here. Okay, and if you drain all that water, then the specific yield means the amount of water in that pore space that can be drained out by gravity. Now question is, if you think of a cup, the inside the pore space is the porosity, and if I just put it upside down, all the water will drain, right? If
Mm.
you ignore the amount of water on the wall. So that's the one is called specific yield, is the amount of water you can recover from the pore space. But now, if you if you do the same thing with a sponge, right? Let's say you put the sponge inside a water and you take it out, and inside that sponge, all the pores are filled with water. So if you just leave it up there, not everything will drain out, right? Because there will be
Mhm.
something will hold up. So anything that drain out in that sponge, so that would be the specific yield. Okay, so specific yield means amount of volume of water drain from that pores divided by total volume. Okay, so that's specific yield. That means the only fraction of the pore space is drained, and the remaining water is
Mm.
stuck inside. That's called residual um, volume, or the um, this is specific yield. Another one is this is a different term we call. Um, so specific yield is this. Okay, so they are not related to porosity. Just
Mm.
specific yield is related to what kind of pore inside it. If it's
Mm.
larger pore, most of them will drain out. If it is small pore, the capillary will hold them together.
Okay. Just a little bit further then. How would you treat the residual water then? Is it just as simple as like introducing a higher velocity, like a force of sorts?
Uh, no, so think of this way. Why they are residual water is because they don't want to drain out, right?
Mm-hmm.
And because the soil itself is holding them together. So if you want to drain them out, what you have to do is you apply the vacuum, which is much higher than the what they're holding together. So it's like the only way to remove that water is applying vacuum
Okay.
at a pressure which is more than they are holding together. It's like, somebody has to pull. You
Mm.
have to apply the vacuum more force than the capillary force itself.
Okay.
If you treat means if you want to remove them, that's what you have to do.
Mm-hmm.
So it's the same thing as sponge. Think of sponge will not drain that water by gravity, because gravitational force or the weight of the water is not sufficient enough to go beyond the pool, or the which the sponge is pulling them together. So that means now, if gravity is not enough, let's say you apply the vacuum, it will shock out everything, right?
Mm.
That's why it does, because it not just the weight of the water, but also you are applying extra force, and that force exceed that holding force. That's how it comes out.
Okay. Thank you.
Let me see if any question let me read any question there. What is the application of measuring the total carbonate and non-carbonate hardness as opposed to using concentration of each species? Um, what is the application of carbonate hardness, total carbonate and non-carbonate hardness? Well, let's think this way now. You have, this is total hardness, is everything, all calcium, magnesium, okay, irrespective of where they are coming from. Carbonate hardness is only calcium that come from carbonate source, right? That's what it means. So the application is this. Every time you think of carbonate hardness, they are natural, okay? Because rock is these rocks dissolve. Okay, when those rocks dissolve, those calcium come from those rocks. Anything non-carbonate hardness, usually they are not natural, or they are something uncommon. Okay, so a lot of times when you deal with hardness where the source are, you are always looking for how much is carbonate hardness, because that's the thing you cannot control. That's something coming from nature. So that's why a lot of times the application is this, they want to look for the cause of hardness of water. Other than that, it really doesn't mean anything else. Because still you have to treat whether it's a non-carbonate or carbonate. What is the application of measuring the total carbon? Okay. Any other questions? All right, so we answer all the questions. So there is a question Ishtar asked, if you have time, can you explain slide 32 on lecture 8? Um, Let me see lecture 832. Okay, so I'm going to stop sharing the laptop screen, but I'm going to share the screen from the slide. So the question was, can you explain this one? Okay, if you're asking this one for a quiz, you don't need to worry about it. But let me explain what this entire slide is about. Here we try to solve how retardation factor R equal to 1 plus bulk density times KD divided by porosity. Okay, so this is the uh, this is the so basically we are doing that not just to derive that why retardation factor is that. But now if you think of conceptually what this means is this is a mass balance equations. Mass balance equation for water on the very top is dc by the mass of pollutants, which is not reactive, is dc by dt inside this block. So if you take any block in aquifer and you want to know how the concentration change inside that block with time, you are saying that that change in concentration, because it's non-reactive, is related to how much things are coming in and how much things are coming out. Okay, so that's the mass balance equation, dc by dt equal to q in minus q out, qc in minus qc out. So basically that term is this term. Velocity time dc by dx is basically that term, because there the flow rate is moving the contaminants. Here you are saying the velocity is moving because you are doing per unit area. So that's how you get this answer. So that there are two terms here in the right side. One is the advections and another is dispersion. So you are saying that net change in concentration inside a block with time is related to how much things move in because of velocity of water minus how much things coming out of the system because of velocity of water, plus how much things coming in because of dispersion of water from dispersion of contaminant from that near zone to here, minus how much leave the system because of dispersion. So that's basically the first the first equation. In the second equation, everything remains same. The only difference is you have to account for amount of contaminant that's also in the soil, because you are talking about how much change in that block. Now you are saying that look, it's not just in water, contaminants are also in soil. So that's why there is a second term related to contaminant in the soil. Then you solve them together. That's how you get the retardation factor. So it's just the mass balance equation, nothing else. Change in time, change concentration, change in a certain location because of time is because of things coming in minus things coming out, especially. All right, so that's all. I don't think I have any other question. I'm going to stop recording.